Okay, so last time, let me check one other thing here, make sure we're all squared up. Okay, so last time we were focused on deriving the equations of continuity, and I showed you how to derive those from a continuum approach using material volumes. We derived the result that is shown in the boxed expression here, and that is basically the equation of continuity for a species. It says that at any point in space, the change in the concentration of that species with respect to time, plus any amount of material that flows into or from that point from any coordinate direction, that is the divergence of the flux, the sum of those two has to equal the net rate of production of component A by chemical reaction. And this is a differential equation that basically states a concept that many of you in chemical engineering would have learned when you were taking material and energy balances. That is that the accumulation of a component in a material volume must be equal to the net rate of input minus output from that control volume plus the rate of generation minus the rate of consumption of that component by chemical reaction. We derived this initially in terms of mass concentrations and then used the relationship between molar and mass concentrations to derive an entirely analogous expression in terms of molar concentrations. And these two expressions in the boxes will be the backbone of our mass balance solutions going forward. And so we'll use these quite a bit as the starting point for our analyses of different problems. We related the component concentrations to the overall concentration of material in a system or in a mixture. Rho, which you would also know as the mixture density, it would be the mass of all of the constituents per unit volume of that mixture. We use that then to define a mass average velocity that appears in the continuity equation, and then also the mass fraction. We summed all of the species continuity equations to get an overall mixture continuity equation, and this is the equation that you probably maybe have first seen in fluid mechanics as the so-called continuity equation. And this is to show you how to get to that result from the mass transfer point of view. We did the same thing with respect to molar concentrations to derive a molar average continuity equation. Very often in transport phenomena where gases are involved, we will use, or chemical reaction, we'll use molar concentration units. So it's helpful to have these equations in molar form. In other situations, it'll be more convenient to use mass fractions and mass concentrations, and so it's helpful to be able to go back and forth. That's a review of where we were last time. Today, we'll continue this a little bit further by describing the definition of mass flux and how that fits into these relationships. We know from our earlier reading that the mass flux of a component A relative to a fixed coordinate system is just the concentration of that component times the average velocity of that component in the system V sub A. So you can always write flux as a product of a concentration and a velocity. And so we can replace rho A times VA in our species continuity equation to get the result that is shown here. That's a direct replacement using this particular definition. And if you were to sum up all of the fluxes in a multi-component system, you'd find that that was the total density times the mass average velocity. Now, very often we split this flux into two components, and we split it into a piece which I'll call J sub A that is the flux of component A relative to the flux of A as it is carried along by the average velocity in the system. And so this would be the flux of A that is above and beyond the flux that you would get just by having A floating along with the system at its mass average velocity. So if you imagine, for example, water flowing through a pipe and you inject dye into that water, the dye is going to move down the pipe due to the flow of the water, just the bulk convective flow of the water. That would be represented by V in this equation. However, the dye can also diffuse if it's in water. And the motion of the dye above and beyond that you get from simple convective motion would be J sub A. And this we will often call the mass flux with respect to mass average velocity, or the diffusive flux. It is this flux, J sub A, that is related through Fick's law to the concentration gradients in the system. And so the total flux is not necessarily, N sub A is not necessarily equal to minus the diffusion coefficient times the concentration gradient, but J sub A is. And very often this difference in the velocity of A and the average velocity is often called the diffusive velocity U sub A. And so you'll see that terminology used in the literature as well. And so if we use this expression to break the total mass flux into two pieces, we have the result that is shown in the box expression here in the middle of the page. And essentially, this just splits the total mass flux into a piece that is due to the average velocity in the system. This is what you would call convection. And a piece that is above and beyond the average velocity in the system. This is what we would typically associate with concentration gradient-driven diffusion. And so there's been no change here except to introduce this definition of J sub A. You can verify, and I think this you may already have done on the homework, that the sum of these J sub A's over all the components in a system is equal to 0. And if you think about it just a little bit, that's the way it has to be. If J sub A is the flux of component A that is above and beyond the average flux in the system, then if you have several components that are, that have an average flux through a system, some of them have to be moving faster than the average and some slower than the average. Otherwise, they wouldn't add up properly to give that average. And so in a binary system, for example, if the flux of J sub A is positive, you can be guaranteed that that of component B is negative and of the same magnitude. And so you can, these diffusive fluxes sum to 0 because they're always written relative to the average concentration. Now, you can extend this concept also to the molar fluxes, and your textbook uses capital letters for the molar fluxes, and so we'll try to stick with that. And basically, the argument goes in much the same way to break the total molar flux into a piece that is relative to the molar average velocity, V star, and a piece that is simply due to the transport of components based upon that molar average velocity. And so the continuity equation in molar coordinates will look like this. Here's the diffusive contribution, and then this is the piece that's due to what we would know is due to convection. You also would find, and you should verify, that the sum of these J sub A's, capital J sub A, is also equal to 0. I showed you a textbook in Slattery last time that has a lot of this laid out, but it's also in your textbook as well. And so this is the basic machinery that we use to conserve mass in all mass transport problems. Now, what we don't have yet at this point is a rigorous and detailed expression for these fluxes, these diffusive fluxes, J sub A, and that will be the subject of another lecture where we derive those. I'm not going to belabor this point because it is of tangential interest to most of the problems that we will solve in this course, but these used to establish these so-called point equations for continuity of species A and for mixture continuity can also be used in the principles of conservation of linear and angular momentum and the principle of conservation of momentum. And you can derive, for example, starting from a material volume, you can derive point expressions for the rate of conservation of momentum. And so you have basically a consistent set of transport equations that demand conservation of mass, conservation of momentum, and ultimately conservation of energy. And these equations can all be derived using the same starting point. And again, we won't spend a lot of time on this, but it's just to make you aware of this methodology in the literature. And for the conservation of linear momentum, we do exactly the same sort of analysis that we did with mass transfer. We write the time rate of change of linear momentum in a body as the sum of the forces acting on that body. And so if you will remember back to your high school and college physics courses, this equation is a statement of Newton's law. The sum of the forces acting on a body is equal to the time rate of change of the momentum of that body. And normally you would see that expressed as mass times acceleration. So this is another way of writing that mass times acceleration is equal to the sum of the forces on a body. And those forces on a material body can be due to forces on the surface. That is, you have traction forces that can be exerted, pressure, for example, that can be exerted on a body. And you can also have forces that are just due to the mass or the characteristics of the material inside the volume. So gravity would be an example of a body force. You can have species-specific body forces. So if you put a saltwater solution in an electric field, if it's sodium chloride, the sodium atoms will go towards one of the electrodes while the chloride goes towards another, and the water is virtually unaffected by the electric field. So that's what we would mean by a species-specific body force. And so we can include effects of magnetism, gravity, electric field effects, and things like that. In this term, pressure and shearing forces are included in the surface term. And again, I won't belabor this, but we can write the forces that are acting on the surface in terms of the stress tensor. And we can, there's an example in here of sodium and chloride in an aqueous solution migrating in an electric field. We can basically apply the same methodology that we used in the mass balance to derive an equation for the conservation of linear momentum. And the result is shown here. We won't use it so much in this course, but I want you to be aware of that, of how this can be derived. This is often accompanied with an expression of what's called Euler's second law, which is conservation of angular momentum. And again, I'm not going to go through the details on that, but it basically turns out that the result of that, for our purposes, is that the stress tensor has to be symmetric in a multi-component mixture. Now, we can also derive the principle of conservation of energy. And again, I'm not going to spend an awful lot of time on this, but you'll see it set forth in your textbook. Basically without an awful lot of explanation. And so you'll have at least a couple pages in here that show you how that is derived. So this provides an expression for us for the to model the concentration inside a system of interest undergoing mass transfer. The mass transport in any system is affected strongly, typically, by what's going on at the boundaries. And so what I'd like to talk about now are so-called jump or interfacial boundary conditions. And so the next little piece of the lecture is based on the theory and a detailed look at these boundary conditions. And one of the most common boundary conditions that we will encounter in chemical engineering is we will have a boundary between two different phases, between a liquid and a gas, a solid and a liquid, a solid and a gas. and we'll be trying to solve for the concentration profile or flux in one or both of those phases. And we'll have to say something about how the concentration and flux, what those variables are at an interface or in the vicinity of an interface. And so again, this is, you'll find the theory outlined in this paper by Slattery. And the basic picture is shown in this cartoon. So we will start again with a material volume. So the entire outside of this particular shape or device or object is a material volume. And we're going to have it basically intersecting a phase interface. So this plane shown here is a phase interface. You can consider the region below it, for example, to be a liquid and the region above it to be a gas. So this would be a gas-liquid interface, for example. And we're going to allow this material volume to intersect that phase interface. And we're going to use the principle of conservation of mass to establish conditions for the conservation of mass right at this phase interface. And this is not particularly helpful or useful in very simple situations, but it turns out that this approach provides a rational and systematic way to establish boundary conditions in situations that are not simple. So for example, we're going to come back and have a closer look at the Stefan tube problem. And in that problem, you have a liquid-gas interface, if you remember, and you have liquid evaporating from that liquid phase into the gas phase. And so that must mean rigorously, if no liquid's being added to that system, that as the liquid evaporates, that liquid level moves down in the Stefan tube. In fact, that was one of the ways that we track and measure the fusion coefficients in the gas phase, watching that liquid level go down. And we made a number of assumptions in the Stefan tube problem, one of which is that there was essentially no convective transport of the gas in the gas of component B, if you will, the non-evaporating component in that gas phase. And the reason for that is we said that the rate of evaporation was typically so low that that the flux of B was essentially negligible relative to that of A. This approach lets you establish a rigorous condition for that boundary condition to evaluate that assumption, and to evaluate under what circumstances it would be true and under what circumstances it would not. And so, for example, if you have that liquid-gas interface, what would be the velocity of the interface? How would that be related to the mass fluxes in the system? That's the kind of questions you can answer with this particular approach. And so we are going to treat this interface, that's the region that is labeled S subsingular, or SING here. We're going to treat this interface as a sharp interface. In other words, at this interface, we have a step transition in physical properties between those of the liquid, for example, and those of the gas. That is, properties like density will undergo a step change at that liquid-gas interface. Now, if you think about this from a molecular point of view, as you came down to an atomistic level, there must be a smearing of that density right at the gas-liquid interface. The density doesn't change rigorously, abruptly there. But it changes over such a small distance that for many practical problems, we can regard that as a sharp interface. And that's where the name of these interfacial balances, we call them jump mass balances, because originally it was expressed that there was a jump in some of the physical properties at that interface, a jump or a discontinuity in things like density going from the liquid to the gas phase. And so we are going to treat this entire volume as a material volume. It has two pieces. V plus is the part of the material volume that is in the gas phase, if we let that be this clear region. And V minus is the part of the material volume that is in the liquid or more condensed phase. Each of those volumes will have associated with it a surface area. And there's no net mass transport of any components across, of any component of interest across that surface area, S plus and S minus. There is also associated with this material volume a surface area associated with the phase interface, and that we'll call the S sub singular to denote that this is the surface where you have singular or you have sharp transitions in the physical properties like density and perhaps concentration and so forth. The entire material volume, that is V plus plus V minus, allows no net mass transport across its boundaries. It's the definition of a material volume. However, V plus and V minus individually are not material volumes because there can be mass transport across this interface. That's one of the things we're trying to get at. Is what is that? What are the characteristics of that mass transport? And we'll define further a velocity of the interface, and I'll explain that here in a little bit more detail. But it is basically the net motion of this interface. And we'll define also two unit normals at C plus and at C minus. At C plus points into V plus and at C minus points into V minus. The outward pointing unit normal from the surface is simply N, as we've used previously. Now, we can write a material balance on the mass density, and we'll let psi for a moment represent mass density. It could also represent, I write it this way because we can also apply the same approach to density of momentum transport across an interface, density of energy transport across this interface. And so this approach can be used to derive boundary conditions, interfacial boundary conditions for mass, energy, and momentum transport. We're only going to focus on the mass transport piece today. And so if we write a balance on for example, mass density, we can write that the time rate of change of the total amount of mass inside this material volume, so that'll just be the mass density times the volume averaged over the volume. The time rate of change of that can be broken up into two pieces, one over V plus and one over V minus. At the end of the day, what is the sum of these two? It has to be zero, right? Inside that material volume, if we're writing balance on the total amount of mass in that, total amount of grams, for example, of material inside that material volume, the time rate of change of that has to ultimately equal zero. So we're going to basically be writing zero in a somewhat creative and complex fashion here. We can apply the Reynolds transport theorem to each of the terms on the right-hand side of this equation, and I'll do it mainly to one of these, and then we'll do the other by analogy. So if we do that in the case of the of V plus, then I can exchange the derivative inside and outside the integral, and as a result of that, we generate an extra term over the surface. One is the mass density integrated over the surface associated with V plus, which is S plus, and then there's also a term that is generated that is the associated with the integral of the mass density on the plus side of that phase interface times the interfacial velocity. And there's a negative sign here because whereas the unit normal N is outward pointing on the outward surface of that volume V plus, we've defined exceed to point into the unit, into the material volume. And what I want to make clear is this term psi plus. If we talk about mass transport, that's going to be the density of the system. And the plus sign means that that is the density at the phase interface, but on the, in this case, the plus side. We call the plus side, just for sake of argument, the gas phase. And so that would be the density right at this phase interface, but in the gas phase. And so you can imagine if you have a liquid-gas interface, just in the gas phase, the density is going to be on order of magnitude 1,000 times less than it is just across that phase interface in the liquid phase. And so we'll make a distinction between the density right at that interface in the gas phase and the density right at that interface in the liquid phase, right? Because they can be very different. And our first integration here only concerns what's going on in the plus phase or the gas phase, if you will, using this argument. We can apply the Reynolds transport theorem to the liquid phase or the minus phase and get essentially the same result. And we can add both of these guys together, and we'll get the result that is shown here. I've used a special nomenclature, these special brackets. We'll see those over and over as we use jump mass balances in the future. And that is just a shorthand way of writing these two terms, that it's xc plus times the local velocity on the plus side, or in the gas phase as we've used in this example, plus the same value of, for example, density on the liquid side times the local density there. And another way of writing it, recognizing that xc plus is equal to minus xc minus. These are unit normals that point in opposite directions. We can write it in terms of one of those unit normals, in this case the one pointing into the gas phase. So this is simply an arbitrary way of writing this term so that we don't continue to carry around all of this baggage with us through the rest of the equations. And so our general expression for the jump mass balance, or for the jump balances after application of Reynolds transport theorem, is shown here. Now, to make that specific to mass balance, we will replace psi with the density of the system in the original equation, and you have the result that is shown here. So C has just been replaced with rho. We can also apply the continuity equation to each volume. We derived last time this expression that d rho dt plus the divergence of rho v is equal to 0 everywhere in any material volume. That's just a continuity equation. And so certainly if we integrate it over the entire volume V plus, this is just 0 integrated over that volume, it will be equal identically to 0. And the reason we do that is because we're going to use this result to subtract out some of the terms that are here and to leave us with the terms that we want. So we can apply the divergence theorem to the flux term, and you'll remember the divergence theorem allows you to convert a volume integral to surface integral, right? And so this converts the integral, the derivative of the flux over the volume, into an integral over the surface, and the surface is broken up into two pieces. S plus is the part of the material volume that's on V plus, and S singular is the surface area associated with that phase interface. And if you think about it just a little bit, what does this term represent physically? The divergence of the flux at a given point. Rika, you have a... Okay, yes, that's the rho times V would be the net mass flux in the system. So what would the divergence of the flux, what does that mean physically? Where the flux goes, okay? And so if you imagine at a point, this is basically telling you what is the divergence is, you know, if you expanded that out into a tiny volume, you know, a cube in Cartesian coordinates of dimensions delta x, delta y, and delta z, this divergence of the flux would be the difference between the rate of input and output to that little differential volume, right, in all the coordinate directions. And if you think about how mass would have to get into or out of a given region of space, or certainly into and out of this material volume, you can't generate mass inside the material volume, right? You can't generate you know, new grams of material inside the material volume. And so any mass transport has to occur across the surface. And if you look at the terms, the density times the velocity dotted into the unit normal, this is basically the net rate of mass transport across the surface and into that material volume, both on S plus and on the singular surface. Now, it turns out, and we'll see this in just a moment, that because V plus, at least all parts of it that are on S plus is a material volume, there'll be no net mass transport coming across that material volume. That's the definition of a material volume. But you can certainly have material enter and leave V plus across that phase interface. And that's what this term represents. This is the density, if you will. If we use the plus phase as a gas phase, it's the density on the gas phase times the velocity of the gas in the direction into the material volume, V plus. Because you'll, if you look back at the picture, back up here a little bit, the only way that we bring material into V plus is if the transport of that material is in the direction of its C plus. If the material is flowing sideways, it's not going into V plus. And so we take the velocity of the gas, if you will, or V plus, and we dot it into its C plus to pick out that component that is taking material into V plus away from the phase interface. And so we can use this rewritten form of the continuity equation in our expression for basically the mass balance over V plus, and the result is shown here. We can apply the same type of approach to V minus, and then we can combine these two results. And essentially we'll have two terms out here that go away when I take this result and subtract it from my jump mass balance, as shown here, over the entire material volume. And what I'm left with is this integral over that interfacial area of the density times the velocity relative to the piece of the velocity that's directed into the material volume minus the interface velocity. Remember that these brackets denote that we are using this definition, and so we have basically that the integral over the singular surface of this term has to be equal to 0. We have defined this material volume arbitrarily, and so we can vary it as we like. The only way we can be sure that that term is equal to 0 for any material volume, any interfacial volume that we might choose, is if this integrand is absolutely equal to 0 everywhere on that interface. And so this is the condition for the jump mass balance. And it says basically that any material that comes to, for example, the liquid gas interface from the liquid phase, any material that comes to the interface has to leave the interface. This particular form of the jump mass balance does not allow for accumulation of material at the interface. Remember, we're treating this interface as razor sharp and razor thin, and so if you take a molecule of liquid at the a molecule of material at the liquid phase and it evaporates, it doesn't stay at that interface. It's either in the liquid phase or in the gas phase. It's not stuck, if you will, at the interface. And so what this jump mass balance recognizes is that the any material that comes to that phase interface from one phase leaves in the other phase. And we'll see an application of it here in just a moment that I hope will clarify its use. You can also apply this to the energy balance. And again, I'm not going to belabor this because we're going to focus most of our attention here on mass balances, but you can derive rigorously a jump energy balance. You can also use the same approach to derive a jump momentum balance. I'll show you that in just a second, but again, we're not going to spend a lot of time on it. I can define the net flux, mass flux across an interface, m dot, as rho times v minus u dotted into xc. And let me explain what that means. If you imagine you're trying to measure, for example, or calculate the mass flux of gas that crosses a liquid vapor interface. And you want to know how much of that material is going from the liquid phase into the gas phase. You might think that it's just the density of the gas times the gas velocity, or that component that's perpendicular to the surface. However, if we imagine this as a glass of water, essentially, that's half full, and the water is evaporating into the gas phase, I can pick the glass of water up and raise it or move it, and that shouldn't be included in the net rate of evaporation of water from that surface. And so this additional term, that is the velocity of the interface, or u, that appears in here, allows the interface to move without having that be a contribution to the net rate of transport of material from one phase to another. Just because you pick the glass up shouldn't mean, the rate of evaporation that you calculate shouldn't depend, shouldn't change if you just pick the glass up and put it from one table onto another, right? And so the mass flux across the interface we're after is the net mass flux above and beyond the motion of that phase interface. This would be for a liquid gas system. This would be basically in the gas phase, the rate of evaporation of that liquid into the gas phase. And so the jump mass balance then is written as the net mass flux to the surface from the plus phase, and that away from the interface in the minus phase have to be equal to one another. This again is a statement of no accumulation of material at a phase interface. Now we'll relax that as we go forward and look at cases like surface diffusion, but this is the simplest form of that, and it's useful in many situations. You can also apply the same methodology to the momentum balance, and you can derive an expression for the rate of transfer of momentum across a phase interface, and it has several components. One is if you move mass from one phase to another, and that mass has a velocity associated with it, well, that moves momentum. from one phase to another. So you can have momentum transport as a result of mass transport. You can also have momentum transport across a phase interface in the absence of mass transport. So if you consider a balloon that's inflated with a gas and it's impermeable to that gas, you can exert a pressure on the surface of that balloon and transfer momentum to the balloon or to the gas inside the balloon without having any mass transfer occur. And so this will have contributions from the stress that's exerted on the phase interface in the direction of the interface. You can also, in the case of momentum, you can produce momentum as a result of surface tension-driven forces, and we won't spend a lot of time on that just now. But the main thing here is to understand that the same approach that we use for mass balances can be used for energy and momentum balances as well. And so I'm going to skip down past the example for heat transfer to one which is related to the, at least conceptually, to the Stefan tube problem, and that is to determine the solid vapor interface velocity in a subliming solid. So if you imagine a piece of dry ice sitting on a table, the dry carbon dioxide converts directly to a gas phase and is transported away from that surface. And so we might ask, what is the net rate of the interfacial velocity? What is the velocity of the gas away from the solid vapor surface? And we can get at those questions, or we can relate those values to one another through jump mass balance. And so if we consider the solid to be stationary, it's just sitting there subliming CO2 into the gas phase. We can write the jump mass balance as shown here. We're going to consider the vapor to be the plus phase and the solid to be the minus phase. And if we expand this term and take the dot product of the unit normal with the velocity, I'm going to pick out the velocity of the vapor and the interface velocity that are in the direction of xc. Those are shown here. In other words, the motion, if you take your dry ice and slide it, and move it around, that doesn't move the solid it doesn't move the CO2 from the solid phase to the gas phase. It's only the transport that is across the phase interface that moves the molecules from one phase to another. And so this unit normal picks out the piece of the velocity that is normal to the surface, the piece of the velocity that contributes to the net mass transport across the interface. And so I will write those velocities as uxc and v into the vapor phase sub xc to denote that it's in this direction of unit normal away from the surface. And so here are the definitions of those terms, and we can define the interface velocity, or we can calculate the interface velocity as shown here in terms of the density of the CO2 in the vapor phase and the solid phase, and the velocity of the CO2 in each of those phases. And if we have the solid being immobile, it's just a frozen solid sitting there, but there's no net motion of it, then the velocity of the solid in the xc direction is 0, and we have this result for the interfacial velocity. That is how fast that interface moves as the CO2 vaporizes. And look what it says. It says that the interface velocity, the density, let's start off here with the fact that the density of the solid will be much greater than that of the vapor, right? And so, and the densities will be positive numbers. And so rho v over rho s minus rho v is a positive number. And the minus sign that comes out here says that the interface velocity must be in the opposite direction to the velocity of the CO2 in the vapor phase. And so essentially as the CO2 vaporizes and leaves that interface, the height of the solid decreases a little bit, right? And so and that interface velocity u sub c is the velocity of that solid liquid interface. And so as the CO2 evaporates and goes up, the interface must go down a little bit. So they move in opposite. The interface moves in the opposite direction to the gas phase. And what is the coefficient of proportionality between them? Well, if we think about the fact that the density of the gas phase, rho sub v, is much less than that of the solid material. So rho s is often much, much greater than rho v. Then I can essentially write this as rho v divided by rho s, right? If rho s is 1,000 times rho v, this term doesn't matter relative to this one. So I can view this as the ratio of rho v to rho s. And if rho sub v is 1/1000th, for example, of rho s, so the vapor density is very much less than the solid density, and let's set it at 1/1000th of the solid density just for sake of argument. Maybe it's 1/500th or 1/2000th, but it's in that range. Then this number is going to be on order of magnitude 10 to the minus 3. This rho v over rho s minus rho v. So it says the interface velocity is 10 to the minus 3 times the vapor velocity. And if you think about that a little bit, every time that you would evaporate or sublime a molecule of CO2, it goes into a gas phase where its density is much less than in the solid. And so you would, the velocity in the solid, the velocity in the vapor phase at very low density to remove material from that surface would have to be enormously greater than the rate at which that interface position changes with time, right? Just because of the density difference between the two phases. And so we would expect that this interface velocity would be much smaller than the velocity in the gas phase, simply because of the density difference. And in fact, when we look back, we'll have a little closer look at the Stefan tube problem after this. When we look back to that Stefan tube problem, what we will see is that the fact that the interface moves very slowly relative to the evaporation of the gas phase velocity allows us to make the assumption that the net flux or velocity of the nitrogen, in the case of the Stefan tube problem, that is the non-evaporating species in the gas phase, the net velocity of the nitrogen in the gas phase is orders of magnitude less than that of the liquid that's evaporated. Because the nitrogen only comes into that Stefan tube to replace any lowering of the liquid level. And so that's going to be, for every, in a sense, millimeter of reduction of the liquid level in that Stefan tube problem, you've created, a meter of gas that has to be moved out just based on the density difference. And so the nitrogen that would come into that tube would, be enough to fill it a millimeter, while the liquid that's evaporating would, basically fill a column that was a meter high in round numbers. And so this lets you, it will turn out to be helpful for establishing boundary conditions like that. It also gives you a rigorous way to relate the interface velocity to the local velocities in the phases around a system. And it shows you, in this particular case, the interface velocity can be orders of magnitude different from the velocity in the vapor phase. And we've said the velocity in the solid phase is 0. So those are those three velocities, the velocity in this case in the solid phase, the velocity in the vapor, and the velocity in the interface are separate and are not at all equal to one another, right? And so this gives you a way to account for complex moving boundary conditions, essentially. And so I'm going to move on from here to talk about a related subject, and that is a phase interface where we will now relax the assumption that there can be no accumulation at that phase interface. And so if we have a phase interface, and now I'll write it as 1 and 2, where 1 is the less dense phase, let's call it a gas phase, and 2 will be the liquid phase that C is pointing into phase 1. We're going to now allow one or more components in these phases to accumulate at the interface, or to adsorb, if you will, at the interface. And this we will use, for example, when we're treating catalytic surfaces and we have components that adsorb and then undergo chemical reaction on those catalyst surfaces. I've shown you how to derive the mass, use jump balances to derive the overall equation for conservation of mass. And I'm not going to walk back through that machinery to derive the species-specific versions of that, but you can find that in Slattery's paper, or I think you'll see that it's derived quite. It has a form that's quite analogous to the overall continuity equation. And so, if you think about on a molar basis, the net rate of transport of a component A from phase 2 into phase 1, we can express that by the equation that's shown here. This is just a slight variation from the one that we derived for the total mass balance, and at the phase interface. It's written in molar coordinates and now applies only to a species, but you can derive that. The other variables use the interface velocity again. And if we define a term lambda A as the moles of A that are adsorbed at that interface per unit area, we can write, I will assert that we can derive, using the machinery that I've just shown you, we can derive a jump mass balance for a surface where we can have accumulation of component A at that surface, and where we can allow component A to undergo chemical reaction at that surface. And the result of that expression is shown here. And it says that the time rate of change of the moles of A that are adsorbed at an interface per unit area of that interface, d gamma A dt, has to be equal to the net rate at which component A is brought to that interface from the two sides, and I'll write this out in a minute so we can see the rest of it, plus the net rate of production of A per unit time and per unit area by chemical reaction. Now, this particular form of the jump mass balance neglects surface diffusion. It assumes that the molecules, when they adsorb at the interface, they don't move around on that interface. You can define a further variation of this where you allow for gradients in the surface concentration of material and allow surface diffusion to occur. We're going to look at a number of cases now, specific cases involving this result. We're going to take, for the time being, that the interface will be stationary so that we don't worry about that in our in trying to derive these very common boundary conditions. And so, if we consider a case, the first case where there's no adsorption at the interface and there's no chemical reaction, we can simplify this jump mass balance to the form that's shown here in equation 3. You'll recall that C sub A times V sub A is, by definition, the total molar flux in sub A at that interface. And so what this means is that if you have no adsorption and no chemical reaction, any amount of component A that comes to the interface from one phase has to leave in the other phase, or the flux of A to an interface has to equal the flux of A away from that interface. So think about, you've applied this probably without thinking about it like this way many times before, right? You establish a boundary condition in a liquid-gas interface, and any liquid that leaves the liquid phase enters the gas phase, right? But the fluxes of the components are matched at the interface. You can also apply that to heat flux, right, at a conductive interface. The heat fluxes are matched at an interface and so forth. Now, when you have the situation where the fluxes are in balance, it also turns out that that's an indicator that interface is in chemical equilibrium. And the condition for chemical equilibrium is that the chemical potential of A in phase one right at the interface is equal to the chemical potential of that component A right at that phase interface. The little m denotes that we're, superscript m denotes that we're using molar version of chemical potential. It turns out that one can also define the chemical potential based on a mass basis, and we'll use that a little bit later. But this is the molar chemical potential that you may be more or less familiar with from thermodynamics. Now, we can write the chemical potential always in terms of a reference, chemical potential plus RT times the log of the activity. This is just a way of defining the activity. And the activity is the way that we typically include the concentration dependence of chemical potential in a given system. Very often we would write that molar-based activity as RT times the log of gamma A times XA, where gamma A would be the activity coefficient of A, and XA would be the mole fraction. You'll remember for an ideal solution that the activity of an ideal solution is simply equal to the mole fraction of that component in the solution. From this point, you can derive, for example, Raoult's law. So this is a very common way of expressing activity. In the polymer world where I work, we typically write the activity not in terms of mole fraction, but in terms of volume fraction, since the molecular weight of polymers are often, you often have a distribution of molecular weights, and mole fraction is not particularly representative of concentrations. So there are other ways you could write the activity, but in gas and liquid systems, this is a very common way to do it. And then you have thermodynamic models that tell you how that activity coefficient depends on temperature and pressure and composition and so forth. For ideal solutions, gamma A is just one. Now I can write XA in terms of the concentration of A divided by the total molar concentration, so I can write this equation as shown here, and then write the expression of component A at the interface in this fashion. Now, I equate the chemical potential of component A at the interface on both sides. So I write the same type of expression, but now on both sides of the interface. And then I calculate from this expression the ratio of the concentration of A at the interface in phase one divided by the concentration of A at the interface in phase two. And it has a term that depends on the reference states. It depends on the ratio of the activity coefficients and the ratio of the total concentrations in both phases. This term on the right-hand side, we typically write as a partition coefficient. This is basically the ratio of the concentration of A in one phase to the concentration of A in another phase, right at the phase interface, and we often call that a partition coefficient. In the polymers world, we would call it a solubility coefficient. So it would be the solubility of a gas or liquid or ion inside a polymer. So it's just, but you see where that comes from, and it comes from the condition of chemical equilibrium at that interface. And so this condition of chemical equilibrium sets K. And we can come back to the fluxes at the interface, and I can write the total mass flux as a piece that depends upon the average velocity, and also a piece that depends upon J sub A. Remember that the total molar flux we broke up previously into a piece that depended on the molar average velocity and a piece that we call J sub A, capital J sub A. Well, for a binary system, capital J sub A is just fixed law, right? So we can replace J sub A with this expression. Likewise, with the flux in phase 2, we can use the expression that's shown here. And so unlike temperature, which across a phase interface is always constant, at a phase interface you can have a jump in concentration. It's the ratio of the concentrations that are constant. It's not the concentration itself that is the same on both sides of the phase interface, but the ratio of the concentrations, or the partitioning coefficient, will describe the ratio or the relationship between the concentration of A in phase 1 and that in phase 2. And so if I have a situation where I have no convective velocity right at that phase interface, and we'll talk about situations under which that occurs. One would be, we looked at this problem of liquid flowing down a wall and calculating basically the rate of absorption of a gas into the liquid as it flowed down the wall. It's a falling film absorber, essentially. And we said at the liquid wall interface that there was no flux of A into the of the components of interest into the wall of that device. Well, that's a case where the velocity in both the solid, that wall, and in the liquid associated, right by it, the velocities there are zero, right? You have a no-slip condition right at that solid liquid interface, and the solid itself is not moving. And under those conditions, the flux of A from one phase must equal that in another. And if you have no transport of a species of interest into that solid wall, then this term would be zero, and therefore the flux of A into that at that interface would be equal to zero. And this is entirely analogous to an insulating condition in heat transfer, where the heat flux at an insulating, at the heat flux across a phase interface, not in an insulating wall, but across a phase interface, has to be continuous. You can put that in terms of Fourier's law, as shown here. So you've seen this analogous expression in terms of heat transfer as well. Now we can also consider a case where the phase 2 is impervious to A, as it would be, for example, with a solid catalyst support. We imagine this as being a flat surface for the time being. And if phase 2 is impervious to component A, then by definition the composition of A inside that solid surface has to be zero. And if you put this into the general mass balance equation, the result you get is shown here. And I can rewrite that using the definition of total molar flux as C sub A times V sub A. I can write it as shown here. And what it says is that the time rate of change of the moles of A that are adsorbed to that surface is equal to the net rate at which A is brought to that surface plus the net rate of production of A by chemical reactions. So there are two mechanisms to change the number of moles of A that are adsorbed on that surface. You can either bring A to the surface or take it away by diffusion or convection effects, or you can have chemical reaction generate or consume A at the surface. And so this reflects the balance of those. And at steady state, the flux is equal to the flux of A at the surface has to be equal to the net rate of flux of A away from the surface has to be equal to the net rate of generation of A at steady state. We've already used this in solving several problems previously. Remember, we had the catalytic surface problem, and we asserted that the reaction set the flux and set the ratio of fluxes at the phase interface. Well, that comes from exactly this point. If we consider a situation where the reaction of A would depend upon the concentration of A at a phase interface, and let's make it a simple dependence. That is, we'll let the net rate of production of A depend upon the surface concentration of A to first order, to the first power. So we'll write R sub A hat. The little hat denotes this is reaction rate on a surface in terms of its rate constant, K hat, times gamma A, which is the surface concentration. And if K hat's greater than 0, you're generating A, and if it's less than 0, you're consuming it. And the concentration of A that's adsorbed on the surface must be related to the concentration of A just next to the surface. In other words, the number of molecules that adsorb onto a surface depends in some way on the number of molecules that are in the phase, that are in the solution or the gas that is just next to that phase. And what we will assume, just to show you how how these types of adsorption models can be developed, is that the surface concentration is controlled by the rate of adsorption and desorption at that surface. And so a simple model of that says that the net molar flux of A to the surface is equal to the difference between the rate of adsorption at the interface minus the rate of desorption. The rate of adsorption we write using this mass action kinetics point of view in terms of an adsorption rate constant. That's a rate constant for A to come from the phase next to the surface and sit down on the surface, times the concentration of A in the phase next to the surface, right? So if you have no A present in the phase next to the surface, you ain't going to get no adsorption of A, right? There's no A to adsorb. Times the difference between the surface concentration of A and the maximum concentration of A that can adsorb to that surface. This is what I would call the parking lot model of surface adsorption. It assumes that there's a maximum number of slots on that surface that can hold A, and the rate of adsorption is proportional to essentially the fractional occupancy of the surface, and proportional to how much A is just next to the surface that's available to participate in adsorption. The desorption model, and again, these can be varied depending on the situation, but this is a simple approach. The desorption model just says that the rate of desorption from the surface is proportional to how many molecules are adsorbed to the surface. So, each molecule has a certain probability of desorbing, and so the net rate of desorption is proportional to surface concentration. And so if we come back to this transient mass balance and insert these expressions for the flux, we can generate this result for the transient mass balance on a surface where we have adsorption, desorption, and chemical reaction at steady state. And in situations where there's no chemical reaction, the only terms that are left are these two. And what that says is that at steady state, at a surface that where a component can adsorb to that surface, at steady state, if there's no chemical reaction, the rate of adsorption to the surface must be equal to the rate of desorption. Right? There's nowhere else for the molecules to go. And I can write this term, the surface concentration of A, I can reorganize this expression in terms of the surface concentration of A, and look what I get. I get that the surface concentration of A depends upon the maximum surface concentration of A, the concentration of A in the phase just next to the surface, divided by this equilibrium constant, the ratio of the desorption-adsorption rate constant plus the concentration of A next to the interface. This is the so-called Langmuir sorption isotherm. where the adsorption, you've seen this, for example, in the adsorption of gas onto a solid surface. And you can derive it. You'll often see this derived in the literature from a thermodynamic point of view, from a starting from a equality of chemical potentials and working from there. We've derived it from a kinetic point of view, basically conservation of mass, assuming a simple model for adsorption and desorption, steady state, no chemical reaction, and you get to this Langmuir isotherm. If the surface, reaction rate is first order, you can include that at steady state. So this provides you a tool with which to model interfacial reactions. So where chemical reaction occurs along with adsorption, desorption, if the adsorption, desorption don't obey Langmuir's model, you can replace those rates of adsorption and desorption with other models that are more appropriate for the physics of the problem under study, and develop expressions that are analogous to but different from the simple Langmuir model. And so this gives us a way to rationally derive boundary conditions and equilibrium partitioning conditions for components between one phase and adsorbed onto a surface. And so with that, I think this is a good place to stop and wrap it up for today.